Okay, so welcome everyone to the second part of today's row. So it's a pleasure for me to introduce Yasmine Beck. So Yasmine is a postdoc at Essex Business School in Paris, France, since November 2024. She obtained her PhD in robust bilevel optimization from Trier University in Germany not long ago, so December 2024. She's also one of the young women for OR, uh, and it's a pleasure to have her here. So without further ado, I want to give the control to you, Yasmin.
Yes, thank you for the very kind introduction and also for the invitation to speak here in this webinar. It's my great pleasure to talk about joint work with Ivana Lubitsch from ESSEC Business School and Martin Schmidt from Trier University about some solution methods for a special class of robust bilevel problems. So what is this talk about? Well, as I said, we will talk about bilevel optimization, which on a very high level can be used to model the hierarchical interaction between two decision makers, which we call the leader and the follower. And these situations where you can apply bilevel optimization arise in many practical applications, especially in the context of pricing, transportation, or energy. If you've been following this webinar closely, you have already come across the fact that bilevel and robust optimization share a lot of commonalities because they both have this kind of multi-level structure. Whereas in robust optimization, the two players are the decision maker and the uncertainty in some sense. In bilevel optimization, it may be considered a bit more general because the leader and the follower actually can be different individual decision makers. However, we're not talking about the connections between bilevel and robust optimization in this talk, but instead, let me talk about problems at the intersection of these two problem classes. And more specifically, we will consider bilevel problems in which the leader and the follower act as adversaries, which leads us to considering min-max type of problems. Moreover, there will be some kind of uncertainty in the follower's problem, and we use techniques from robust optimization to tackle them. More specifically, this will lead us to so-called robust min-max problems with a here and now follower, because we will consider the timing in which the leader acts first, then the follower decides while taking the leader's decision into account, and afterward, the uncertainty may realize. So the follower has to decide here and now before the uncertainty realizes. And for these kind of problems, we will consider two types of solution approaches. One is an exact branch and cut method, the other one a heuristic framework. But let's make this a bit more formal, and let's start with the deterministic problem setup. So in this talk, we will consider bilevel problems in which on the so-called upper level, we have the leader's problem, and the leader controls the variables x, which may be mixed integer in our setting. Moreover,
Yasmin,
yes.
it might be something technical. We only see now the title slide.
Oh, okay.
I
Wait
hope
a
that we
second.
haven't missed a lot.
No.
Okay.
Thanks for making me aware of that. So let me maybe take a different viewer. Sorry about that. I wasn't aware that this is happening. So,
I'm happy that I brought it up then. And
yes,
also,
yes. Thank
Yanis, I
you.
think at the same time put it in chat. So
So wait. Yeah, I also didn't see the chat. Sorry for that. Let me try again with a different device. So you should see some, slides again. Now in full screen mode. And now,
yeah,
whoop, now it should
yeah,
also switch, yes?
yes, yeah.
Okay. So what you missed in the last 2 minutes was basically just a summary of what I already said. Sorry about that. So we will consider robust min-max problems with here and now followers, and we will consider two types of solution methods, an exact one and a heuristic one. And this is the deterministic problem setup. So we will consider bilevel problems in which the upper level is the leader's problem, and here we have the leader's variables x, which may be mixed integer. There may also be some other constraints on the leader's variables, which we capture in the set capital X here. But in principle, this could be anything. But here we focus more on the linear settings, so some linear inequalities maybe. Now, in addition to these variables X of the leader, we have another set of variables Y, which are the variables of the follower and which have to be an optimal solution to a nested optimization problem. And this is the so-called lower level problem or the followers problem. What is special about this min-max setting here is that we have the same terms depending on the followers variables, both in the upper and the lower level objectives, but that we optimize them into opposing directions. Throughout this talk, we make some standard assumptions so that an optimal solution to this problem actually exists. Namely, we assume that the so-called shared constraint set is non-empty and compact, and that all linking variables, that is, all variables X of the leader that appear in the lower level constraints, are assumed to be bounded integers. Moreover, in this talk, we will focus on the setting in which the lower level is a binary or a combinatorial problem, so that we only have binary variables Y for the follower. Due to the nested structure of these bilevel problems, they are intrinsically hard to solve. So when developing solution methods for these problems, what one typically does first is to reformulate them as a classic single level problem. And here in our setting, we do this using the so-called lower level optimal value function. So here, one evaluation of this lower level optimal value function phi corresponds to solving one X parameterized combinatorial optimization problem. So up to now, the setting that we consider is purely deterministic in the sense that we do not take any kind of uncertainty into account. But as I mentioned in the beginning, we are actually interested in the case in which there is some kind of uncertainty. And to be more specific, we are studying the setting in which the lower level objective function coefficients f are uncertain but known to take values in the given interval, which is specified by the nominal value and the maximum deviation from the nominal value. To hedge against these kind of uncertainties, we use a gamma robust approach, or the discrete budgeted uncertainty modeling that we have just seen in Dorothee's talk, so that the follower only hedges against at most gamma many deviations in the coefficients that adversely affect the objective function value of the follower. So overall, this will then lead us to the so-called gamma robust counterpart of the lower level problem that you can see here. Now, the overall gamma robust min-max problem is obtained by replacing the deterministic value function with its robust counterpart, so that in the following, we will consider bilevel problems that take this form. Even in the deterministic setting, these min-max problems are sigma 2p hard in general, and I see that we have some experts on the topic here in the audience as well here. Especially also Lasse Wolf was in this webinar, I think 1 month ago. So if you're interested more in the complexity theoretical aspects of these problems, you should definitely watch the recording of his talk. We are more interested in the algorithmic aspects of these problems. And let me talk a bit about how we could solve these gamma robust min-max problems in principle. So after some reformulation tricks using strong duality, one could reformulate this gamma robust min-max problem as a mixed integer linear bilevel problem. And for these problem classes, there are currently 2 solvers out there that can be applied. The first one is the so-called MIPS solver, And the second one is a branch and cut framework by Fischetti and co-authors. However, these reformulations that are needed to apply these methods typically lead to significantly larger models, so that even for very small instances, they run into the time limit and we cannot tackle these instances. So to remedy the situation, what we do is we propose problem-tailored approaches. And the first one is an exact branch and cut framework. And the second one will be a heuristic, which actually does not require that much of problem tailoring. Both of these methods, they rely on a famous result by Bertsimas and Sim for gamma-robust single-level problems. So let me recap this for you here. To apply this result by Bertsimas and Sim, we explicitly need the assumption of only binary variables for the follower. And in addition, we have a technical assumption regarding the deviations in the objective function so that they are given in non-increasing order. Given these assumptions, we can now apply the famous result by Bertsimas and Sim to our lower level problem, or the gamma-robust counterpart of the lower level, so that the overall problem can be solved as the following. And here, don't let the heavy notation scare you. Just keep in mind that the gamma, delta, and also the F bars are all parameters that are known to the follower. So overall, what we consider here in these inner maximization problems are deterministic objective functions over the same set of constraints. So what this means is that we can solve the gamma-robust counterpart of our lower level problem by solving cardinality of L many deterministic lower level subproblems. And with each such subproblem, we will associate its own value function. And in the following, I will just drop the cardinality off and make it a bit more short and say we solve L many lower level subproblems of the nominal type. Now, with this being said, let's move to the first solution approach, which is an exact branch and cut framework. And the method works as follows. So here we have our gamma-robust min-max problem. And the first step towards solving it is now to introduce an auxiliary variable so that we can shift the value function from the objective into the constraints of the problem. So this is very much like Bender's decomposition. What we then do is we solve a relaxation of this problem in which we drop the value function constraint in star, and we also omit the integrality restrictions on the leaders variables. A solution to this problem is then most likely not feasible for our original problem, which we verify in two checks. The first one is to check for integer feasibility, that is, to check if all the integrality restrictions are satisfied. If this is not the case, you can either branch or add your favorite valid inequalities from single-level mixed integer optimization to separate this point. Afterward, so if the solution is integer feasible, we proceed by checking for bilevel feasibility. And this means that we have to verify if the constraint in star is satisfied, so that we have to solve the parameterized gamma-robust lower level problem for the fixed leaders decision X star. And as we have just seen, this can be done by solving L lower level subproblems that are all parameterized in X star. If there is at least one such subproblem for which this inequality is not satisfied, this means that the current solution is not bilevel feasible, so we have to add a valid inequality to separate this point. And overall, after branching and adding valid inequalities, we get a refined problem formulation, which we solve again, and we repeat this procedure until we find an integer and bilevel feasible point. There are some general purpose inequalities that can be used for separating bilevel infeasible points, but typically it's beneficial to exploit the specific structures of the bilevel problem to obtain stronger formulations. And as an illustration, I will show you how this can be done for an important subclass of these min-max problems, which is the class of so-called monotone interdiction problems. So what does render a min-max problem a monotone interdiction problem? We make some assumptions, namely that the upper level objective does not include terms depending on the leader's decision. So C is the zero vector here. And for simplicity, we also assume that we only have binary variables for the leader here. Moreover, the lower level feasible set has a specific structure, namely that there may be some linear inequality constraints which are completely independent from the leader's decision, so that the upper and the lower level problems are only coupled via so-called interdiction constraints. And these interdiction constraints give the leader the ability to prohibit the usage of some variables by the follower. So using the first two bullet points here renders our min-max problem an interdiction problem. Now, we additionally assume that the lower level side satisfies the so-called downward monotonicity or hereditary property. And to ensure this, we assume that the parameters that describe the linear inequality system in the lower level problem are all non-negative, so that we get the following implication. If we have a lower level feasible vector y that dominates another binary vector y prime, we can already conclude that this vector y prime is feasible for the lower level problem as well. And these monotone interdiction problems, you can find them in many packing type applications and also in the context of critical infrastructure defense. And for these problems, let us now have a look how we can derive problem-tailored cutting planes. And the idea is the following. So on the left, we have one of the lower level subproblems for a fixed index L. What we do is we now propose a penalty reformulation of this problem in which we drop the interdiction constraints and instead add penalty terms to the objective for their violation. And under our given assumptions, we can show that both of these problems admit the same optimal objective function value, so that we can exploit this fact to restate our value function constraints. So now, instead of having the original lower level subproblems on the right-hand side of the inequality, we now use the penalty reformulation here. Why are we doing this? This penalty reformulation is actually quite nice because the feasible set does not depend on the leader's decision variables x anymore. And for fixed x, we have a linear objective function. So what we know is an optimal solution to these penalty reformulated problems will be attained at one of the vertices of the convex hull of the feasible set. And this fact already leads us to our so-called interdiction cuts, which take this form. So we have the objective function here, and y hat is the set of vertices of the convex hull of our feasible set. If we embed these cuts into the branch and cut framework that we have seen earlier, we obtain a method that terminates with a globally optimal solution after finitely many steps. But still, the method may not perform too well, which is why we also came up with several enhancement techniques to further improve the performance. But I'm not showing you the results here today, but instead, let me move on to the second solution approach for gamma robust min-max problems, which is a heuristic in the spirit of the famous Bert-Siemers and Sim result. Just a little refresher. This is the bilevel problem that we have considered so far. So here we have L many value functions in the constraints of the problem. When developing our heuristic, we now propose to consider L bilevel problems instead, in which we only have a single value function constraint in the model. In particular, each of these bilevel subproblems is now one deterministic min-max problem and also a relaxation of our original gamma-robust min-max problem. So what we can draw from this is that an optimal solution to this problem, or the value of an optimal solution to this problem, yields us a valid lower bound for our original problem. Moreover, we can also use the x part of the solution, plugged it into the gamma-robust lower-level problem to obtain an upper bound for our overall gamma-robust min-max problem. And putting this into an algorithmic framework already leads to our heuristic. So we start by initializing the leader's decision and our bounds. And afterward, we solve L-many deterministic min-max problems. We sort these problems so that their optimal objective function values are given in non-decreasing order. And the one with the largest value gives us the best lower bound. The next steps are then used to compute upper bounds. And to this end, we iterate through all of our subproblem solutions. We plug them into the lower level subproblems to compute the optimal objective function value of the gamma-robust follower. If the leader's objective function value is better than our current incumbent, we update the bound and also the best found leader's decision so far. Overall, we repeat this procedure until we have either investigated all of the subproblem solutions or until our optimality gap is closed. What's nice about this framework is that we compute both primal and dual bounds, and that any solver for deterministic min-max problems can be used in line 3, and any solver for deterministic combinatorial problems can be used in line 8 of the method. Moreover, the subproblems that we consider in these lines 3 and 8, they are independent of each other, meaning that if we have the capacities available, we could also solve them in parallel. However, there's also a drawback to the method, namely that we have to solve L deterministic min-max problems, and in the worst case, up to L squared many deterministic single-level problems. And this is done both to global optimality. And let me emphasize here again that the deterministic min-max problems are still sigma 2p hard in general. So from a complexity theoretical point of view, the problems that we solve are actually not easier than our original problem, but they're typically much, much easier to solve in practice. But anyhow, it's evident that our framework requires a significant amount of resources, especially if our index set L is large. To remedy the situation at least a bit, we also developed several conditions under which we can omit the solution of some of the subproblems. And here I would like to mention one result, namely that we have several conditions under which we can terminate with a globally optimal solution after line 3 of the method, so that we actually can solve the gamma-robust min-max problem by only solving deterministic min-max problems. So this is then a natural extension of the Berzima sim result for the single-level case. With this being said, let's have a look at some computational results. So we implemented both the exact and the heuristic method in Python and Gurobi. And to evaluate them, we consider instances from the knapsack interdiction problem that we have adapted to account for a gamma-robust follower. And here I'm showing you the results for 560 instances, and each of these gets a time limit of 1 hour. We will consider 4 different solution approaches for these instances. The first one is the exact and problem tailored branch and cut that we have seen in the first half of this talk. And the second 2 are variants of our heuristic. Here, let me emphasize again that we can use any solver for deterministic min-max problems in our framework. And for our study, we consider 2 options. The first one is the BKP solver by Weninger and Fukasawa. The second one is a branch and cut framework for monotone interdiction problems by Fischetti and co-authors. Finally, we also have a benchmark heuristic that we compare to, which is the greedy interdiction heuristic by Scott and Negre. And at least to give you an idea how this works, first, the leader picks an interdiction policy in a greedy-like fashion. So we pack a greedy knapsack. Afterward, this interdiction policy is plugged into the gamma robust lower level problem to compute an upper bound. However, the method does not provide a lower bound, so that to have at least some kind of comparison, we solve the so-called high point relaxation of the bilevel problem, which in our setting here just is equivalent to setting a lower bound of 0 for the knapsack case. And this is the result that we get. So here we see the box plots for the four considered approaches with respect to running times. And the run times in seconds are given on a log-scaled axis. What we can see here is that the greedy interdiction heuristic significantly outperforms all of the other methods in terms of the running times. And in fact, this is actually not really surprising because the greedy interdiction heuristic only solves single-level problems, whereas all remaining approaches, in addition, also solve bi-level problems. But anyhow, among the other approaches, we can see that the heuristic which uses the BKP solver still performs significantly better than the remaining two approaches. And especially we have significant speedup factors when we embed the BKP solver in our heuristic framework. So what we can learn from these figures is that it seems to be the case, and this is also true, that solving the deterministic min-max problems, so bi-level problems, is the bottleneck of our framework, and that the choice for the solution method for these problems is crucial for the overall performance of our method. But still, we are comparing heuristics with an exact approach here, so let me also show you some results regarding the quality of the solutions that we obtain. And here on the right, we again have box plots with respect to optimality gaps of our methods. And again, we can see that especially the heuristic uses the BKP solver significantly outperforms all the other approaches in terms of solution quality. In particular, we could show global optimality for almost all of the considered instances, and you can see very small optimality gaps for the remaining ones. So overall, what we can say is that if we have efficient black box solvers for the deterministic bilevel problems available, then our heuristic can outperform the benchmark approaches, both in terms of the running times and also the solution quality. And with this being said, me briefly wrap up the entire talk. So we have seen gamma robust min-max problems in which we use the famous result by Betsimas and Sim to deal uncertainty in the lower level objective function. The first part of this talk was about an exact branch and cut approach, also with tailored cuts for the special class of monotone interdiction problems. And if you're interested into the details, then you can find the preprint, or not the preprint, but the paper is at MPC. Also with a more general approach that does not rely on the binary assumption of the lower level. In the second part, we then saw a heuristic that is very similar to the famous result by Betsimas and Sim, so that we solve a linear number of deterministic min-max problems. And now, in addition, we also solve additional single-level problems to obtain upper and lower bounds. Any solver can be used here for solving the deterministic problems so that no problem-specific tailoring is required. And we have seen in our computational study that the method can outperform benchmark approaches, both exact and heuristic, if we have efficient black box solvers available. The paper is going to appear in Inform's Journal on Computing very soon. And one last part maybe, if you're interested into this topic more, a possible direction for future research could be to develop alpha approximation algorithms for deterministic bilevel problems that could be embedded into our heuristic framework. Because as we have seen, solving the bilevel problems to global optimality is the bottleneck of our framework. And with this being said, that's all from my side, and thank you for listening.